Okay. Yeah.
Okay. Yeah. So we are ready for the second part of today's seminar, and we are very happy to have Benedict von Harling, who will tell us about baryogenesis from a relaxing Higgs.
Yeah. Thanks a lot for the invitation. I'm particularly happy not having to talk to a screen for a change. So this work. Yeah. So this is. I'm going to talk about work based on two papers. Is Enrico Morgante, who's also here with us. And as the title suggests, this is about a baryogenesis mechanism that involves the production of gauge fields. And the idea is that I will discuss two implementations. One case with an axion-like inflaton, and another implementation with a Higgs, which has a large expectation value after inflation. And in both cases, I will assume a coupling of the scalar field to the Church-Simons term of hypercharge, so YY tilde. And as we'll see in a second, this will lead to the production of helical hypercharged gauge fields, which under certain conditions can survive until the electric phase transition, and will then be transformed into a baryon asymmetry. And we'll discuss this. Yeah, and this is the outline. So let me skip this. And let me get straight to the mechanism. I will start with the case of an axion-like inflaton because it's a bit simpler. And then in the second part, I will talk about the relaxing Higgs that the title promises, actually. So I assume this coupling of the axion photon to YY tilde. I should say that this cannot be the decay constant of the axion that determines the inflaton potential, because this decay constant needs to be super Planckian. And in order to get a strong effect, this parameter here needs to be sub-Planckian. So one needs a connection like in the clockwork or something, where you have two parametrically different decay constants. Okay, so assuming this coupling, now we can determine the equation of motion for a momentum space for the gauge modes. And I see that the equation of motion is modified by this term here, where lambda is the helicity of the mode in question, so +1 or -1. And psi is essentially the inflaton velocity divided by this parameter f and the Hubble constant. And then you see that essentially if psi is positive, then modes with positive helicity and momentum smaller than psi will have a time and will be copiously produced, whereas modes with the opposite helicity will not be produced at all. And this leads to the production of a net. So helicity is just defined as the product of the gauge field times hypergauge field times a hypermagnetic field. Essentially just counts the power in positive helicity modes minus negative helicity modes. In case you wonder, this quantity is gauge invariant up to boundary terms. And if I choose the volume large enough, I can just ignore these boundary terms for all practical purposes. Okay, so and now the observation or the main point in this scenario is that that the production of magnetic helicity comes with the production of a B+L asymmetry due to the B+L anomaly. So if you see the anomaly equation contains this contribution from hypercharge, and of course also one from the W from the SU2, but for now this will not play a role. So now if I go to the zeros component and integrate over space, I find an evolution equation for which symmetry is equal to the derivative of the helicity.
Sorry, I was wondering, do you not get Schwinger suppression from fermions?
Sorry?
Do you get fermions being produced?
Exactly, yeah. So
is there no suppression then of the gauge field production?
Exactly. So yeah, I will come to that later. So exactly this. Yeah, I will discuss this later.
Thanks.
So okay. So the basic point is that if I change my hypermagnetic helicity, I also induce a change in the B plus L asymmetry. Out by Shaposhnikov and collaborators. And I mean, this can be intuitive, and if you notice that the time derivative of the helicity is really just the product of my hyperelectric field times the hypermagnetic field. So if I have a non-zero time derivative of the hypermagnetic helicity, I have a non-zero product times B field. And then the production in a tree can simply be understood as Schwinger-like pair production in a strong electric and magnetic field. And it's actually nice because you can turn the argument around. Like pair production, and then you get this relation. So then, based on this result, the sequence of events in our scenario will be the following. So initially we produce.
Can I ask a very dumb question? So you're saying it's a Schwinger effect, but isn't this equation basically a one loop equation, whereas the Schwinger effect is non-perturbative, or maybe am I wrong?
Schwinger, sorry. Yeah, I'm not. I mean, there's also a quantum effect, right? So
yeah, but isn't it non-perturbative? And
good question. Yeah. No. I mean, it has. I mean, it has two. I mean, okay. I simplified it a bit. It also has a non. I mean, it also has a non. Another contribution that doesn't contribute to the B plus L anomaly. I mean, there is additional fermion production, but it doesn't contribute to the P plus L asymmetry. Mm-hmm. But then, yeah, there is a production which produces asymmetry. Yeah, I'm not sure. So sorry.
Sure.
Okay, so the sequence of events now is that initially we produce a non-zero hypermagnetic helicity, but at the same time we also produce a B plus L asymmetry. And these things are really like essentially two coins of the same thing. We haven't actually effectively produced anything yet at this stage. So then universe. So this takes place. I mean, the dominant production happens at the end of inflation. Then the universe reheats, and at some point, electric sphalerons go into equilibrium, start to erase this B plus L symmetry. And there's actually a process that that can turn the B plus L symmetry back and erase the chiral plasma, and one has to be careful that this doesn't happen. I will say a bit later. I will talk about this. Okay, so assuming that this chiral plasma instability doesn't happen, the plus L symmetry will be completely washed out by the sphalerons, and then I only have this hypermagnetic helicity left. And then under certain conditions, this hypermagnetic helicity can survive until the electric phase transition. I will also talk about which conditions these are, and will then be converted into a baryon asymmetry, as I will now discuss. So, yeah, the basic point is that at the electric phase transition, electric symmetry is broken, and the hypermagnetic fields will be, or the helicity in hypermagnetic fields will be projected into helicity in Z bosons, which quickly decays, and another helicity component in ordinary magnetic fields. And the point now is that since the U1 of electromagnetism is vector-like, it doesn't contribute to the anomaly. So effectively this projection of the hypermagnetic fields into ordinary magnetic fields means that that the helicity on this side goes to 0. And then by the anomaly equation, there will be a compensating B plus L asymmetry that is produced.
Sorry, can I ask? I think I'm missing the big picture. So this happens. The production of these gauge fields is at inflation, or so oh, I see. And then inflation ends, and they remain until
exactly. And then there's some conditions that you have to fulfill for them to survive until the electric phase transition. So this is not sure. I come to that. So I now made a jump
But their wavelengths are tiny, right? Their wavelengths are.
Yeah, the wavelengths are of order the inflation scale. I mean the co-moving wavelengths. Right?
I see. Okay.
Exactly. Okay, so yeah, the point is that this conversion sources a Baryogenesis asymmetry, and this is a smooth process. And the point is that non-engaged fields obtain so-called magnetic masses, which screen magnetic fields due to some non-perturbative effects in the thermal plasma. But ably engaged bosons don't get such masses. So now, I mean, qualitatively, I can think of a mass matrix, and it's very rough, like for W3 and the hypercharge gauge boson. I mean, so the W3 will get this mass of order the temperature squared. The hypercharge gauge boson will get no mass, and then at equilibrium symmetry breaking, there are also off-diagonal terms of order the Higgs wave squared. And initially, the temperature is much larger. So we're assuming the standard model here, right? So we have a smooth crossover. So initially, the temperature is much larger than the Higgs wave. So these off-diagonal terms are kind of negligible. And then eventually the temperature drops and the Higgs wave grows, and I'm rotating. So yeah, and you can kind of describe this rotation of the hypermagnetic fields into ordinary magnetic fields in terms of a temperature-dependent Weinberg angle. And this has been studied using lattice simulations. And here are some results. So there's the temperature versus this effective mixing angle. Yeah, and you see it's quite messy. I mean, so what we will do is essentially just put some analytic curves through this mess, and then try different possibilities. I mean, this introduces a big uncertainty in this scenario. Okay, so the electric crossover takes place, and the hypermagnetic helicity is turned into ordinary magnetic helicity, which acts now as a source term for the B plus L asymmetry. And the source is really proportional to the time derivative of this effective Weinberg angle. At the same time, of course, the sphalerons is also active and erases asymmetry. So it's a competition between these two processes. But the sphalerons freeze out at 130 GeV. And typically, I mean, now it depends on these curves that I had on the slide before. Typically, there's still a significant enough source at this time, which kind of then leads to a non-zero Baryogenesis asymmetry which survives. And this has been studied in these two papers by Harder and Long. Okay, any questions or?
How sensitive is it to those curves?
Sorry?
How sensitive is it to those curves that you showed?
I can show you later. I mean, quite sensitive. Yeah. I mean, orders of magnitude. I mean, so yeah, in this whole business, the uncertainties are very big so far. But I mean, you could get rid of these uncertainties by now doing better lattice simulations, for example, right? So okay, so yeah, as I said, so I jumped, right? I jumped from inflation straight to the electric, but of course, a lot of time passes in between. I have to make sure that the hypermagnetic helicity doesn't decay somehow in the meantime. So once reheating takes place, the hypermagnetic fields start to interact with the thermal plasma and put it into motion, and then the thermal plasma backs reacts on the hypermagnetic field. And this is described by the field of what is called magnetohydrodynamics, which essentially Maxwell's equations plus the Navier-Stokes equation for the thermal plasma for the velocity field. Typically for non-relativistic plasma velocities, the electric field changes very slowly. So then I can eliminate it from the equations, and I get an equation purely for the hypermagnetic field, which describes essentially the decay of the hypermagnetic field due to the interaction with the plasma. So there's one term which due to the finite conductivity of the plasma, so sigma is the conductivity, and another term which is due to the velocity field. Yeah, now I can make a rough estimate of the size of these terms if I just assume some typical length scale, wavelength scale for my hypermagnetic field, which, as I said before, is of order the inflation scale. I mean, the co-moving length scale is of order the inflation scale in our scenario. Yeah, then I can estimate these two terms approximately like this. And then the second term will dominate over the first term if the magnetic Reynolds number, which is this combination here, is bigger than 1. Yeah, and I mean, so the velocity field I can estimate from the Navier-Stokes equation, and then I have an analytic expression, analytic estimate for this magnetic Reynolds number. And the point is that if this magnetic Reynolds number is bigger than 1, one expects the helicity to be conserved due to a process that's called the inverse cascade. Now this again has been seen in numerical magnetohydrodynamic simulations. But to get an idea why this happens, you can just look at the time derivative of the helicity, and you plug in your Maxwell equations, and you see that the velocity field drops out. And only this diffusion term here of this hypermagnetic helicity. But now if this magnetic Reynolds number is bigger than 1, the velocity field actually dominates the decay of the hypermagnetic helicity. So essentially this term will play a role. Yeah, what happens, I mean, how you can see this is that, I mean, this inverse cascade, essentially what it does is it transfers the hypermagnetic helicity from smaller to larger and larger wavelengths, which means that this decay term, which of course is still present, never becomes important. So this is, okay. Okay, now I have to, yeah, unfortunately this business is a bit, involves a lot of plasma physics. So now I have to discuss another effect, which goes under the name of chiral plasma instability. So yeah, as I said, so in principle, the sphalerons successively erase this B plus L asymmetry that was generated together with a hypermagnetic helicity. The last asymmetry to be erased is the one in right-handed electrons, because the right-handed electrons talk to the sphalerons only via the left-handed electrons, and the Yukawa coupling of the electrons goes into thermal equilibrium only at temperatures of order 10 to the 5 GeV. So above temperatures of order 10 to the 5 GeV, the asymmetry in right-handed electrons cannot be erased, so it's still present. So let's assume we had higher temperatures, then we can ignore the Yukawa interactions. And then again, from the anomaly equation, you get an equation like this, charge electrons. And so essentially what it tells you is that you can convert one to the other. So what this can do now is that if such a conversion process takes place, the charge asymmetry in electrons creates hypermagnetic helicity, which is equal and opposite in sign to the helicity that is already there, and then essentially erases the whole thing. So, sorry. Yeah, and that this can be possible, you can see by some simple scaling argument. If you just look at some gauge field configuration that can absorb this charge according to this equation, and then you see that if the wavelength of this configuration becomes large enough, at some point it will have lower energy than the energy stored in this asymmetry. And then essentially you can have this process that the charge asymmetry is turned into this hypermagnetic helicity. And again, this has been found. I mean, this can be seen explicitly in magnetohydrodynamic simulations. So this is not something that's just based on some heavy arguments, but you see so. Okay, so essentially now, so this process can happen for gauge field configurations that are sufficiently large, right? Which means that they take some time to form. So you can associate a temperature with this process. This chiroplasma can happen only when the temperatures are dropped to a certain value. Then, yeah, you can estimate it. And essentially then what you have to require is that this temperature is lower than 10 to the 5 GeV, because if it's lower than 10 to the 5 GeV, the sphalerons will already have erased the whole B plus L asymmetry, the whole fermionic asymmetry that was there. And so this process is not a danger anymore. Okay, and here's kind of a summary plot of the picture. So we have inflation, and we generate the helicity, and well, in principle, it's a whole P plus L asymmetry in different fermions, but I mean, the asymmetry that survives the longest is the one in right-handed electrons. So that's the one that is depicted here. Yeah, and so if this magnetic Reynolds number is less than 1, the helicity will diffuse away. If it's larger than 1, the helicity will most likely survive. Also, if this chiroplasma instability happens, it can erase. I mean, it can turn, as I said, it can turn the charge, the fermionic charge asymmetry into helicity with equal and opposite signs. So it can again erase the helicity. Yeah, but I mean, if it doesn't happen until temperatures of order 10 to the 5 GeV, the asymmetry will be erased, and we have the helicity surviving on the electric scale. Okay, and this is kind of the results for the case of axion inflation. And yeah, I don't want to discuss all the details. I mean, the main message here is that the plots have a huge amount of uncertainty. And one uncertainty comes from what you were asking earlier, that the production of the fermions together with the magnetic fields will back react on the gauge field production and slow it down. And then it's unfortunately not possible to solve this analytically. So what we did is just we relied on some two possibilities that seem reasonable how this back reaction works, which correspond to the left plot and the right plot. Yeah, and so you see that so this is the inflation scale, where this psi parameter is essentially the inflaton velocity at the end of inflation. And you see in the green regions is where you would get baryon asymmetry. The red curves are, you have to be below the red curves to avoid this chiral plasma instability, and you have to be above the blue curves to have a magnetic Reynolds number bigger than 1. So yeah, but the main message here is that the uncertainty is big, so it looks like it could still work. It could work, but you definitely need. So first of all, you need a better understanding of the factory crossover, these lattice simulations, to reduce the uncertainties. So these uncertainties are essentially like the width of these bands here, due to the uncertainties from the electroweak crossover. And then you also would need dedicated magnetohydrodynamics simulations to understand better the conditions on this magnetic Reynolds number and from the chiral plasma instability.
So I have a question about the inflationary part of this. And you're assuming an inflation where it couples to the hypercharge.
Mm-hmm.
So what about how do the perturbations look like? Do these hypercharge modes contribute to I don't know, B modes, or well, just in general, what does the spectrum look like?
Yeah, so I think it exactly. So I think it can lead to non-Gaussianities, and then essentially you get a constraint on this psi parameter, but not at the end of inflation, but essentially when the
but you're producing them throughout inflation, right? So
exactly, but I mean, of course, I mean, essentially you get an upper bound on this psi parameter. 60 e-folds before inflation, roughly, right? When the visible modes are produced. I don't remember now. I mean, I think it has to be less than 1 or something. Yeah, and then, so we assume we allow here for the possibility that this parameter at the end of inflation is larger, because of course, in the meantime, the field could accelerate a bit. So
yes, yeah.
So
but I mean, it's also interesting just for prediction, right? Like it could.
Yeah, exactly. I mean, we haven't really looked. I mean, we haven't looked much into this. I mean, but I mean, it's kind of also separate. I mean, there's a whole literature on this, kind of where people study this. But yeah, again, it's also a little bit decoupled, right? Because I mean, one depends on the psi parameter, 60 e-folds or something before the end of inflation. Whereas what is interesting for us is the psi parameter at the end of inflation. Right? So
yeah. Okay, makes sense.
But yeah, I mean, it would be interesting to have some signals. I mean,
I see there's a question on Zoom.
Yeah, hi. Sorry, getting back to the amount of back reaction in this setup, since you have, so now your hypercharge is just getting generated tachyonically during inflation, and in order for that back reaction to be under control, then your parameter psi cannot be very large. So at most it can be around 4 or 5. Unless you will generate so much gauge field that will stop inflation. So,
I mean, no. I mean, so this is I mean, of course. So essentially, I mean, you see, like these parts of the curves is where the back reaction is still negligible, and then if you go above parameters psi of order 4, the slope of these curves changes exactly because of the back reaction. So because the back reaction kicks in and you produce less gauge fields. So this is, I mean, this is, yeah, we essentially used this estimate from my collaborators, Valerie Domke and Kyoi Mukaida. So they worked this out in another paper and came up essentially with these two possibilities, but I mean, it is, I mean, there are big uncertainties in this. So, but in principle, the attempt is to include the back reaction. So this, does that answer the question?
Yeah, because I'm familiar with this calculation. That's why I mentioned that. So these calculations are based on solving linear equations.
Exactly. So exactly.
Production is tachyonic.
Yeah.
And so it means after a while, then if psi is large enough, it wouldn't be linear anymore. In fact, it would be badly nonlinear. Yeah, and then so the back reaction, at least up to the point that it's I mean the linear approximation for gauge field production works, then that's how we actually drive the value of psi that it cannot exceed 4 or 3 or 4. But after that, then it needs a full numerical study because it's badly nonlinear.
Sorry, I mean, yeah, I mean, exactly. So these are nonlinear equations, right? So you cannot solve them exactly, right? So then you have to make some reasonable assumptions, which then leads to these two scenarios. I mean, I agree this can be approved. I mean, it's not the end of the story. So, but in principle, the back reaction is supposed to be taken into account in these plots. So this is.
Right, sorry. So if I just can add one last comment, then based on these two plots, it seems that your setup can generate enough baryons once the reheat temperature is very high, and it's around God scale, right? Because that's the limit that when psi is small enough and gauge field production is under control in inflation, still you can explain baryon asymmetry.
Yeah, exactly. So, I mean, of course, I mean, like the preferred region is in the region where you actually have significant back reaction, right? So this is, so again, I mean, I think, I mean, the takeaway method should, I mean, it seems like the scenario can work, but I mean, a lot more work is required to actually establish this. I mean, the nice thing is that this is purely based on standard model physics, essentially, right? So, well, the only beyond the standard model thing is this coupling of the inflaton to the hypercharge. With some dedicated studies, you can actually shrink these error bars and possibly even falsify the scenario. So it could be that not remains in the scenario. It's just not possible. Okay, I think I should go on. Okay, now come to the second part, namely, yeah. So in the first paper, we considered an axial inflaton as a driving field, and now in my latest paper, we were looking at the case where the Higgs is a field that evolves and leads to the production of hypermagnetic fields. So what we assume is that we have a coupling of the Higgs doublet squared again to the Chern-Simons term of hypercharge, and if you're interested, I mean, we have a possible UV completion for this coupling in the appendix of our paper. And we also assume that the Higgs has a very large expectation value at the end of inflation. So it's very far away from its minimum today. Okay, so then electric symmetry is actually broken, right? So, the field that will be dominantly produced is now the photon or ordinary magnetic field. So you can replace this coupling. Yeah, but then, so we assume that this production process happens, so we assume there's inflation, and then there's a period of inflaton oscillations. So a period of matter domination where the temperature is very low, because if the temperature is high, it would back react on the production of the gauge fields. So in order to and essentially completely suppress the production, so in order to not have this problem, we assume that there's this period of inflaton oscillations, a period of matter domination, where the temperature is very low. And then this coupling leads to production of ordinary magnetic fields. Then reheating takes place, and then the electric symmetry is restored, and these ordinary magnetic fields are converted into hypermagnetic fields, and by means of the normal equation, again, B plus L anomaly. B plus L symmetry. And then we are essentially again in the same starting point that we had for axion inflation. So there's not much difference here.
Benedict, I have a question. Is there no issue with CP here? Because CP, because that is a pseudo-scalar operator, and that is a scalar operator.
Yeah,
you're not violating maximally CP.
I mean, the scale is very high, right? So it's yeah, we have some benchmark points. It's 10 to the 15 GeV here, so I think should be fine on it.
So you don't have any CP, largely CP violating effects at low scale apart from the one that you're mentioning, essentially.
Exactly, yeah, yeah.
So
I mean, the scale is very high, right? So, I mean, you can, yeah, I think this is strongly suppressed. Any effects from this coupling? Okay, so so now we need some model to get a large Higgs wave, and what we came up with is, I mean, it's probably other models. I mean, the simplest we came up with is this. So so first of all, in the Snell model, the Higgs quartic coupling runs to negative values, right? So there's like an abyss. To avoid this, we couple the Higgs to some new scalar. And the whole purpose of this scalar is just to avoid the quartic coupling from running negative. So here's like some example, the quartic coupling of the Higgs versus the RG scale, and you see it always stays nicely positive. And to induce a large VEF, we couple the Higgs to the Ricci scale, link to the Ricci scalar. Okay. Yeah, and so just to give you an idea what we need for kind of VEF we need for the Higgs initially. It turns out the most important constraint is again this magnetic Reynolds number to allow Helicity to survive until the electric scale. Yeah, and I mean, if you work it out, you find this big suppression factor, and then it's proportional to the energy density in the hypermagnetic field after reheating, and the square of the correlation length. But these parameters are all, I mean, this is also of the order of the inflation scale. So in the end, you see that what you need to compensate this big factor is like an energy density that is much bigger than the force power of the inflation scale. And then by energy conservation, you immediately see that you need a Higgs VEF, which is inflation. So this is essentially what you learn from equation. Okay, so if it's the case, then two things. First of all, the extra scalar is very heavy because of this cross coupling here. So it is essentially just a spectator. I can just set it to 0, and it just enters the the evolution via loop effects to the quartic coupling. And the Higgs is also very heavy, so as you will see in a second. Okay, so then essentially the potential reduces to Ricci scalar. Another point is that the Ricci scalar comes with a negative sign and will induce like a tachyonic mass term for the Higgs. So this tachyonic mass term and the quartic coupling, so I have a minimum at large Higgs wave. But now the size of this mass term is of order. Wait a second, where do I? Yeah, so okay, so during inflation, I meant that the Ricci scalar is given by this expression, and then during the subsequent phase of meta domination that we assume, the Ricci scalar is given by this expression here, where h is a Hubble rate. And as you see, this doesn't connect continuously. So at the end of inflation, this is a slower parameter. I mean, at the end of single field inflation, this parameter is 1. So this evaluates to something like -6 times h inflation squared, where this is -3 times h inflation squared. So there's like some kind of discontinuity. This this essentially, so how the Ricci scalar changes from this value to this value now depends on the details of the inflation model that we don't want to consider. So instead, what we assume is that we'll assume two different possibilities, either that this change is rapid, so that the Higgs cannot in the minimum, or that it's very slow and that the Higgs can follow the evolution of the minimum. So essentially, in the one case, the Higgs at the end of inflation is still given by this expression here at the onset of meta domination, and in the other case, is given by this expression. And then we also assume, so we also consider two possibilities for, so in single field inflation, at the end of inflation, this epsilon parameter is 1 by definition. But you can also have a scenario like hybrid inflation, where epsilon is still small at the end of inflation. Okay, so anyway, this gives you like 3 different possible initial conditions that don't matter, change much, but a little bit. Okay, so so we have considered 3 benchmark points now, so the suppression scale of this coupling to hypercharge is of order 10 to the 15 GeV, as I was saying before. And now the not so nice part about this is that this psi parameter, this non-minimum coupling to the Ricci scalar, has to be quite big. It's kind of,
Sorry, no, how much longer do you need to finish?
I'm almost done, yeah. Almost done.
So let's say five more minutes?
Even 2 or so. Okay. Yeah, so I need this non-large, non-minimal coupling parameter. So psi is this parameter that parameterizes the non-minimal coupling to the Ricci scalar in order to use a Higgs wave, which is much larger than the Hubble rate at the end of inflation, right? So, okay, anyway, I can, and this was necessary to ensure that this magnetic Reynolds number is bigger than 1, and that these magnetic fields that are produced can survive until the electric phase transition. Okay, so then we have done some numerical simulations for these 3 benchmark points with these 3 initial conditions that I was mentioning. Yeah, and essentially the point is that for these benchmark points, you can produce the observed baryon asymmetry. But as you see, I mean, there's a whole, there's like, essentially all we can say is that the baryon asymmetry is like within this relatively big range. And this is again due to the uncertainty from this time-dependent Weinberg angle. Okay, yeah. And so that's it. Thank you.
Thank you. Sorry, so I think I didn't understand the Higgs relaxation. So what is the model there? It's, I mean, I understood there's a non-minimal coupling of Ricci to the Higgs.
I mean, exactly. So there's again a non-minimal coupling to the Chern-Simons term of hypercharge. But now, we have the Higgs wave at the end of inflation is very large.
Mm-hmm.
And then the Higgs relaxes to its like essentially to its minimum today, right? And during this relaxation process, during this movement of the Higgs, the hypermagnetic fields are produced. So this is essentially.
I see. Okay, I think I understand.
So I think I have 2 questions. So one, what was the motivation to look at this second model with the Higgs actually? I mean, the other one seems more appealing.
Exactly,
no?
I agree. Yeah, so essentially we tried, I guess
I mean,
what we learned from this is that it definitely works much better with the axion inflaton, right? Exactly.
So yeah, I mean, does this?
I mean, the idea was simply that, I mean, okay, no, there are 2 scalar fields essentially, right? One is inflaton and the other is a Higgs. So let's try to also make it work with the Higgs. But yeah, I agree, it doesn't. I mean, this big non-minimal coupling is ugly, I would say, right? I mean, we also comment on another possibility where cross-coupling between the Higgs and the inflaton, then you can also induce a large wave. But then the dynamics is much more complicated, so that's why we didn't elaborate on this. So that in principle, you can, so I think you should, I mean, if that bothers you, this big non-minimal coupling, then there should be ways to make it work without this. I mean, but yeah, but I agree, axion inflaton is much nicer. So
sorry, can I also ask you another quick question? You mentioned these papers by Kamada and Long, right?
yeah.
With what? I mean, I remember those papers. I mean, I remember reading those papers. I don't remember anymore what they were. I mean, compared to you, they were not discussing the mechanism to generate these helical hypercharge fields, or what was the difference? I mean,
Exactly. So they didn't.
They were just assuming that there were helical magnetic
Yeah,
fields.
I mean,
That's
they were mostly focused on solving
on the baryogenesis mechanism.
I mean, solving these the evolution equations for the charge asymmetries.
Right.
Exactly.
So really,
there was then another paper by Kamada, Schmitz, and 2 others.
Yeah.
Which then put it, yeah, then focused on this on the baryogenesis mechanism more concretely. But what they didn't take into account was the fact that you produce the charge asymmetry, this P plus L asymmetry initially together with the hypermagnetic fields, again by due to this anomaly equation. And they also didn't take into account the back reaction from this production process. So this was essentially what we then included in our paper, how we improved it.
Yeah, thank you.
A quick thing, the fact that the Higgs relaxes to its today minimum during electroweak symmetry breaking. This is too small to be relevant, or?
Sorry.
I mean, the Higgs is at 0 before electroweak symmetry breaking, and then relaxes to 100 GeV.
This is definitely way too small. Okay, exactly. Yeah, so again, we need like initial Higgs waves of order. Yeah, what is it? 10 to the 16 GeV or so, right? So this is And again, this you need to pump enough energy into magnetic fields to allow the helicity to survive. I mean, this.
Another question about the first scenario. So in that case, can the inflaton be made into the dark matter candidate?
For axion inflation,
Yeah, with this FF dual. I mean, this thing gets rid of the abundance, right? So maybe there's a hope.
yeah, this could be. I don't know. We didn't think about this. Yeah, so yeah, this would be interesting. Maybe. You mean because it damps the evolution?
Yeah,
and
because
so
the
you don't-
coupling to the
you don't overclose it.
the gauge modes.
Yeah. Okay. This.